Hello Slyfox community. In this video we are going to see how to design a PFD, which is a phase frequency detector, which is used in PLL or phase locked loops. For this project I've used 180 nanometers CMOS technology, which is related to TSMC, and in order to simulate the reference voltage and the divider voltage and signal, I've used pulse voltage sources. And in order to evaluate the performance of my PFD, I've used a transient simulation. Now we are going to see the internal schematic and circuit of our PFD. To do that, you need to select your PFD and then select this icon, which is push into hierarchy edit. This is the schematic of my PFD, and here I want to tell you how to create symbols of your schematic so you could design your whole system in hierarchical arrangement. When you finish your schematic, then in this panel, which is Advanced Design System, the main window, it's enough to select your library and cell and then click this new symbol window. And by selecting it, you could choose the name of your cell and create your symbol as you wish. And whenever you want to use your symbol in your schematic, for example, for simulating, let me go back to here. It's enough to select this icon here, which is for opening the library browser. And in workspace libraries, you could see all the symbols that you've created. I'm using a TSMC 180 nanometer CMOS technology as well, and I've used these components for my main design. And when you create symbols in your schematic, you could go to workspace libraries, PLL-lib, and here you could see all the symbols of the schematics that you've created. And in order to use them, it's enough to select them, drag them, and drop them in your schematic, and as you can see, another PFD is created. But we don't want to do it for now. Let's go back to our schematic. As you can see, our PFD is consisted of two D-latches which are resettable and an AND gate. The AND gate's inputs are the outputs of our D-latches. It takes them, ANDs them, and creates reset pulse. This reset pulse is connected to reset pin of our D-latches. Our PFD takes two inputs, reference and divider, and creates two pulses for us, up and down. These pins will be connected to our charge pump. Now we are going to see the internal schematic and circuit of our D-latches. To do that, it's enough to select it and then click this icon here in order to edit and see the schematic. And whenever you were finished with your design and checking the schematic, in order to go back to upper hierarchy, it's enough to select this icon and you go back to your main schematic. You could do it as many times as you want. This is the schematic of our D-latch, which is resettable. This circuit exists in Razavi's PLL book. You could check it there. It is consisted of 4 NOR gates. And as you can see, the connections are a little bit complex, but with a little patience, you could complete it easily. Our D-latch takes 2 inputs, reset and clock, and it doesn't take any data as input. It is always set to be VDD or digital logic 1, and it creates the output, which is Q for our D-latch. Now let's check the internal schematic of our NOR gates. As you can see, I've used 2 NMOS transistors in parallel with each other, and they take the inputs. And here is the complement of our NMOS transistors. I've used 2 PMOS transistors and they are in series. VDD is set to 1.8 volt, which is connected to here. As you know, this is the necessary voltage for 180 nanometers technology, and this output here generates the NOR of our inputs. Let's go back to the latch. We already checked the schematic of our NOR gates, And that was the required circuit for our delatch. Now let's see the internal schematic of our AND gate. As you can see, again, I've used CMOS topology. Two NMOS transistors are used in series to create NAND gate, and two PMOS to be the complement of this circuit. And this circuit so far creates the NAND gate for us. In order to make it to AND gate, we need to invert the output, so we could get the output as AND gate from this node here. Again, as you can see, VDD is 1.8 volts. Now let's check the internal schematic of our inverter, which is a NOT gate. I've used an NMOS and its gate is connected to a PMOS transistor. One NMOS transistor, one PMOS transistor, and here we can get our output from here. AND gate, PFD, and here is our simulation test bench. In order to simulate the reference and divider, I've used pulse sources, and these are the parameters. The low voltage is set to 0 volts, high voltage is set to 1.8 volts, no delay, rise and fall time are set to 1 picoseconds, the period is set to 15 nanoseconds, and its width is 25 nanoseconds. It is almost the same for the divider, but here we have created a delay of 10 nanoseconds to be able to evaluate the performance of our PFD. And here is how I've set the transient simulation to be. Start time is 0 and stop time is set to be 200 nanoseconds. Maximum time step is set to 1 nanosecond. And by pressing this gear, you could do your simulation. And this page will be opened for you. In order to see your waveforms simultaneously, you could select this stacked rectangular plot and place it here and select your nodes, which are divider, down, up, and etc. I've already done it, and you can see the reference waveform, divider waveform. And as you can see, when our inputs are not in phase, the up voltage creates pulse for us to indicate that our inputs are not in phase and they're different from each other. And as soon as our inputs get in phase, for example, both of them are digital logic 1, our down node creates spike, so that up is pulled down. Our divider is sensitive to both rising edge and falling edge, and it works just fine, and we can use it in our phase locked loop and PLLs without any problem. If this content was useful for you, don't forget to give it a thumbs up and subscribe to our YouTube channel for more electronics content. The next step for this project may be designing the whole PLL, which is consisted of PFD, low pass filter, VCO, divider, and etc. Good luck!